So ladies and gentlemen, I welcome you to this second session by Dr. Asiya Khan from University of Plymouth. Yesterday, we had our first session. I must add here that these training sessions are taking place under this British Council funded project, Undergraduate STEM Education in Pakistan. Our audience today are faculty members and graduate students who are prospective faculty of STEM fields, let's say they're future faculty of STEM from the Department of Physics and Chemistry. And yesterday our session was highly beneficial to the audience where, we learned about equity, diversity and inclusion. And today is our second session. But I will, even though I, know most of you are aware of our resource person, Dr. Asiya Khan, about whom as I said yesterday, I'm in particular very proud because, she's amongst the very few females whom we had as resource persons during this project. And the reason behind that, of course, primarily, one of the main reasons is that women are in general, there are less women in these STEM fields. So we're very proud to have Dr. Asiya with us, and she has a special status amongst all our resource persons because she's one of the very few female resource persons that we have. Earlier, as I added yesterday, that earlier, we had a training session with Professor Dr. Zora Nazir-Kiani, another female in the STEM field whom we're very proud of. So I'll very briefly again introduce Dr. Asiya for those participants who are just joining us today and weren't there yesterday. Dr. Asiya Khan is an associate professor of multimedia, communication and intelligent control at University of Plymouth. She's a chartered engineer and a senior fellow at Higher Education Academy. She's the associate head of teaching and learning in the School of Engineering, Computing and Mathematics, and was previously the Equity, Diversity and Inclusion lead. She led the school to a successful Athena Swan Bronze Award in 2018. So with that, I welcome Dr. Asiya. And I would request you to, again, very briefly introduce yourself again, that even though we did that yesterday, but of course we have participants today who hadn't joined us yesterday. And before for inviting Dr. Asiya, I will again acknowledge and thank British Council for this project, Undergraduate STEM Education in Pakistan, which I'm leading from LCWU side, as this project has enabled us, to carry out these wonderful training activities. So over to you, Dr. Asiya.
Okay, well, thanks, Dr. Aksa, for the kind words and the kind introduction. Assalamu alaikum to everyone. It is morning here, afternoon over there. Well, it's very hot here. I don't know what the temperatures are like. I think it's global warming. We're probably all suffering a little bit. Yes, so I will do a couple of things first. Let me start the recording. So that's the
recording in progress.
Cloud. And let me share my presentation, then we can make a quick start. Yes. So for those of you who weren't here yesterday, a very brief introduction to myself. So I did my BEng honours, so Bachelor in Engineering from University of Glasgow in Electrical and Electronic Engineering. And then I did my MSc from Strathclyde University, which is also in Glasgow. That is north of it. That's north. It's in Scotland, so it's south of Scotland, but Scotland is basically north of the United Kingdom. And after I graduated with my masters, I then worked in British Telecoms, which is a big telecommunication company. It's an international company. And I worked there primarily in the area of communications. I mean, that's what they sort of specialize in. So with payphones and then internet payments and basically products over the internet. After that, we moved from London. So we were in London at the time. We moved from London to a place called Plymouth, which is on the southwest coast, right at the south west of the United Kingdom. And where I then enrolled in the University of Plymouth, did my PhD from there, and subsequently got my permanent tenure position in 2015 at the university. So I was the EDI lead from 2016 to 2019, and in that role, so in the UK we have organisations like the Athena Swan, or I think Higher Equality Commission it's called, where Athena Swan kind of sits in, Race Equality Commission as well. So these are organisations that sort of work towards EDI agenda, and Athena Swan in particular works towards the making the gender balance in STEM subjects, because there is a recognition that in STEM subjects there are less females across the pipeline. So our department and universities committed towards improving female participation, and hence I had that role. We are now working towards a silver application, because the award is initially for 4 years, and then you can kind of go for either a renewal of the award, or you can go for progression. So as the title suggests, that silver, bronze is the starting point, then you go to silver, then you go to gold. And just to give you an idea, I think only 2 or 3 departments, it's not a single university, but 2 or 3 departments in the UK have got a gold award. So they do take it very seriously. And then I became the associate head for teaching and learning in the university, and that is since 2019. I'm in that post. I'm also a chartered engineer, so that is from a professional body. That's a recognition of your contribution to engineering and leadership. And I'm also a senior fellow of the Higher Education Academy, which is an institution that sort of looks at pedagogic research and the sort of like teaching and scholarship that you are doing towards your higher education. So in a way, I'm one of those people who the university is wonderful. They allow me to do what I want to do. And I kind of dip my toes into lots of different things rather than just focus on a single thing. So I do my field research, and I'm going to talk about that today. But I also do other things like support students and do research in that field, especially related to activities with EDI and promoting those. So that was a brief introduction about myself, and just to progress from there, just trying to find something. Today I'm going to focus on AI, being artificial intelligence and computer vision. And I do hope, I appreciate that you guys here are studying physics and chemistry, but there are areas of both of those subjects that sort of like overlap. Chemistry very much with materials, because in mechanical engineering we do a lot of like material science research, and there is a lot of innovation within that. So there is that overlap, I think, with chemistry, especially when you're looking at postgraduate, not perhaps with undergraduate, but with postgraduate study, and obviously with physics, there are a lot of areas that do overlap with engineering. So in terms of my outline, I want to give you a little background about my own research before I kind of delve into artificial intelligence and computer vision, and briefly touch upon autonomy as well. Because like I say, I do a lot of different things, and my research has evolved from where I started from my PhD to where I am today. Okay, so my PhD video quality assessment and prediction. So I did my PhD I started my PhD in 2016, and I completed it in 2021. So I did it part-time. And sorry, not 2016, what am I talking about? I started my PhD in 2006, so I'm 10 years out, and I finished it in 2011. That's it. So just to kind of put your minds back, that it just shows you how much technology has accelerated. Because when I started in 2006, iPhones were just about sort of like, I think they sort of came on the market a little after that, or they were just around there, and they had very small screen, but 176 by 386 by 176, I think, something like that. So very small screen, very small resolution. And this whole concept of having applications on your phone where you are using the internet and making your phone something more than just a text message or a phone call was something which was just sort of, taking over. And hence my PhD research was very much linked with that. So it was linked at that when you have smaller screens or handheld devices and you are streaming video over those handheld devices, there is an issue of quality because the bandwidth is limited. But it's a massive area of network engineering, traffic engineering, and it's sort of evolving as the bandwidth is increasing. But there is always a trade-off. Why there is always a trade-off is because even though the bandwidth has increased, but then the requirements of the consumer are also increasing in terms of what they want to stream. I applied supervised and unsupervised machine learning within my PhD, but that is an area that I very much continue to work in. So I don't work very much with video now. I'm working more with images, and that's like a journey, a personal journey that I have taken. But obviously, machine learning, artificial intelligence, that is something which is very much if you like, in vogue. Everything that we are doing is, we're generating a lot of data because the processing power of the computer has improved significantly. The ability of algorithms to learn from that is improving, and that's the idea of machine learning. So machine is learning from the data, is continuously updating and improving. So that is something that I continue working with. Deep learning is relatively new, and my own involvement in that is relatively new. So I've worked with neural networks, I've worked with fuzzy systems, but obviously deep learning is evolving neural networks in a certain way where you have a number of convoluted layers. And it's basically the arrangement of neural networks where this whole concept of deep learning is materializing now. Computer vision, like I said, I started from video, I'm very image, and so computer vision or machine vision is something that I am very much interested in and have got some live projects that I will share with you later on. Obviously, artificial intelligence is a big umbrella that covers all of that. And in addition to that, there is also guidance and control of unmanned surface vehicles. I mean, I teach control systems. My specialty is more intelligent control, so I do have some sort of limited research in that area as well. And this is in addition to the pedagogic research that I do, for example, looking at underrepresentation of females in engineering, looking at how we can help minority groups to sort of like do better and reach their potential. So that sort of like areas of research is a kind of a slightly different thread to what I'm doing here. I've also looked at cloud computing and sort of image qualities within cloud computing. Okay, so I thought it might be probably more appropriate if I sort of start from my PhD. Sorry, I think I would mute all. I have power. So I'm okay. So I thought I'll start from my PhD journey because that sort of gives you a background of my research and where I'm sort of like coming from. So when I started my PhD, I did have a break because obviously I did my master's many years ago, and I started my PhD in 2006. So there was a break in the middle. I had worked in industry, so I was sort of like coming back into academia and study. And my PhD was very much, like I say, about sending or assessing the quality of video that is sent over a wireless network. So what you see here is there is a network in the middle. So the network could be your fixed IP network like the internet, or access networks that we have like mobile networks like 3G, 4G, and beyond. So you have on the sender side, so this side here, you can all see the cursor. So this side here is your sender side, and this side here is your receiver side. So on the sender side, you have raw video. Now, video usually is very large in size. So what you do is you have an encoder. So you encode the video, packetize it, and then over the network, you send those packets. At the receiver side, you depacketize it, decode it, and then you have you should have the same video that was sent. But what happens is the network introduces some errors and degradation, and hence what you get here is like a degraded video. What you want to do is you want to see how much that video is degraded, and the way video quality is measured intrusively. So what I mean by intrusively is that you need access to raw video. So what happens is you have raw video, you have your received video, and then you compare the frames of each of the send and the received, and then you calculate what is called the peak signal to noise ratio, PSNR, and that gives you an idea of video quality. But the problem with that is, in real life, you will not have access to your send video. What you receive is a video, and if that video is degraded, you need to be able to assess the quality of that video, and then what the consumer would expect is for you to improve that quality to an acceptable level. And hence we have a metric called mean opinion score. So mean opinion score is like a perception metric, and what it does, it basically, you play a range of videos to a number of participants. They don't know what the sender video was. They just looked at the received video, and then from the received video, they will give you a score. The score is from 1 to 5, 5 being excellent and 1 being poor. And then based on those scores, you can assess, because that is the quality as perceived by the user, because there was a shift from doing objective metrics to subjective metrics, because something like video is very subjective. So it was felt that it was, by the ITU, which are the quality standards, that they are setting up the quality standards for these metrics, that it is important that the video is measured as perceived by the user, and hence the mean opinion score kind of comes in. So the idea then is, can you have a prediction model that does not need the raw video? So my prediction model that I proposed and developed during my PhD was a prediction model which was based on quality of experience. So we use the word quality of service. That is very much related to network engineering, and it's very much an objective metric. Quality of experience is like one step away from quality of service, and it's a subjective metric, and it's based on the mean opinion score. That's really the idea here, that you have this metric which sits at the sender side. It looks at the received video. It then decides, has the quality fallen below a certain threshold? And if it has fallen, then you have a feedback mechanism that then does something to the video, either inserts frames or reduces the sender bit rate. The quality can be adjusted to that acceptable level, and for that I used fuzzy logic. The other thing I also did in my PhD is I found a way to classify the contents, because before you can apply the model, there was this recognition that the type of content that is streamed is very different. So for example, you can have a sporting type video, which is very fast moving images, or you can have something like a news type video, which is head and shoulders, a bit like me just now, person talking, and there's very little movement. Or you can have something which is somewhere in the middle of the two. So if the content can be classified before the model is applied, so then the model can be efficient in terms of telling what the what the quality is, and then if the quality is falling below a certain threshold, then obviously to adjust the quality. So obviously, a lot of my work has been published, and what I've done is wherever relevant, I have put the relevant papers. So if you want to have a look in more detail, you can have a look and you can read more in the paper. Okay. So just going back in there, so these are the 3 blocks here, and I will just spend a little bit of time on these blocks. What is content classifier there, because that was one of my contribution, how the model works and how the feedback mechanism works. So these were the 3 blocks here that are at the sender side, and you know, it will spend a bit of time on these blocks, explaining them in slightly more detail. So in terms of the content classification, the way the contents were classified is you have raw video that sort of like comes in, and within the video you have your spatial features and your temporal features. So it is trying to like define each of these features in terms of like some metrics or measures, and then based on that you would then estimate what the content is and then define the content type. So the way I went with the content type is I sort of like split the content type into like a fast moving video, a very slow moving video like Head and Shoulders, and something which was in the middle. So I measured the temporal features. They were measured in a clip, and they were given by what is called the sum of absolute difference, or the SAD value, and that's what how the temporal features were calculated. The spatial features were very much around blockiness that you get in a frame, blurriness, and brightness. So these were the 3 metrics that I used, and they're usually done when you are comparing the current frame to the previous frame. And the content type estimation was done using unsupervised machine learning. And unsupervised machine learning, one of the methods there is called cluster analysis, and there are 2 types of cluster. The 2 types that I used for cluster analysis was hierarchical cluster analysis and k-means cluster analysis. So this is an example here of your cluster analysis, and the way the content was classified here is, and this is an example of k-means. Is like you've got a slow ST, spatial temporal activity, medium spatial temporal activity, and high spatial temporal activity. So I used 9 videos. So they were these are like publicly available videos that at the time the researchers were using. I mean, obviously, like I say, this is a field which is exponentially developed, and so a lot of this is then changed, and it's basically reflected as more research comes in. Then the sort of like what is available for researchers also changes. So this is what was the gold standard at the time. These were the videos that were defined as fast moving. So for fast moving, we had things like a rugby match, a football match, that sort of like activities. And for slow moving, it was just Head and Shoulders, women talking news, as they call it. I can't remember the whole kind of details. So there were 12 videos there, and based on my cluster analysis results, so there you can see the name of the 12 videos, and these names were specific because these were the names given by the researchers, which was publicly available database. So you can then replicate the research, because one of the thing about research is when we publish a paper and we publish our results, it's very important that those results can be replicated by other researchers who are sort of like, coming after you, because one of the things we say in this community is really we are standing on other people's shoulders, and that is only possible if we are using if we are referencing everything, so you can see what we have really done. So the things written here about co-phonetic coefficient and the data split, so that is something which is very much a feature of cluster analysis. So within cluster analysis, you then find a good percentage. Now 80% was considered good. I mean, obviously you would want the percentage to be as close to 100, but 80% was considered good. And based on that, you can see here how these clusters are formed with these videos. And so based on that, the classification was done to say, hey, that's the classification of the spatio-temporal activity of the contents. And when I initially did this work and that was published, I did get a best paper award in an international conference. Because at the time, I think it was very novel to use unsupervised machine learning within the context of content classification. So here again, this is the concept of the overall model. I think block diagrams usually help. Perhaps maybe I use more block diagrams because I teach control systems, and control systems is very much, it takes all your systems and it converts each system into a block, which then helps to model that system either in an equation or in some other form. So what it's really saying here is you have your raw video. So the video comes from, so basically, again, this is going back to the OSI model. I think it stands for Open Systems International. So that's a model which is given for communications. So for communications, you have like a layered model, 7 layers. At the top layer, you have application layer, and the bottom layer, you have physical layer. And then in the middle somewhere, you have the network layer. So basically, we're all users of the internet. The internet sits somewhere between the network layer and the layer below, which is, I think, the data link layer. So it's how this digital communication works. So how you then packetize an information, and then that is then sent. So there are protocols that dictate that those standards of communication. So from the application layer, which was the top layer, that's where the sort of, as the name suggests, the application layer, that's where the application sits. So my application was video. So from there, I chose some parameters like the content type, center bit rate, and the frame rate of the video. And then from the physical layer, that was coming from the access network, I chose things like the packet error rate, the mean block rate, and the block error rate. I think that was the blur was for that. And that went into my regression-based video quality prediction model, and then out came the MOS, or mean opinion score. And again, the novelty in my work was that at the time, the video quality algorithms that researchers had proposed were either just strictly based on the application layer, or they were strictly based on the physical layer. There was, to my knowledge, there was no work that was trying to combine both the application layer and the physical layer. And obviously my model combined parameters from both of those layers. So again, just to give you a little bit more detail, in there is that with the from the application layer, the frame rate and the content resolution. So this is 176 by 144, and then there were some sender bit rates there in kilobit per second for the videos, and then the physical layer parameters, which is the mean block error rate and the mean burst length there. So for the subjective test, because like I say, the gold standard or the benchmark at the time was to do subjective tests, which were the perceptive tests as perceived by the user. So what I did is I set up a subjective test experiment where I recruited people from within the university in a controlled environment, and in that environment I had prepared some videos and then asked people to rate those videos in a sort of like giving a score from 1 to 5. And the database that I produced was, I think, the second one at the time, and that is then became publicly available for research community to use. And this just gives you a histogram of my MOS or mean opinion score subjective database there. And then, like I said, it was a regression-based model. I mean, I did do neural network as well, but it's just to give you a feel of sort of where I've come from. For my regression-based model, that was the model equation that I used to calculate the MOS. And for the content type, the content type obviously was a function of the spatio-temporal features, which is what it says here, SAD, the sum of absolute differences, edge blurriness and brightness. And the MOS, you can see, it's got some parameters there, but the metrics or the variables here are the sender bit rate, content type, the block error rate, and the mean burst length. The correlation that I got was around 93%, and that was pretty good. I did validate my results with external database, and like I said, there was only one external database. I think there might have been two external databases that were available, and this one was the live database, and that was, I think, a university in America that had done that, and so it was based on that. So I haven't added all of those details because I want to kind of spend more time on my current research. But just if I just go back and then I'll come back to that. So basically, that was the model, that was the content classifier that we've done, and then I'll just briefly talk about the feedback mechanism, and then I'll kind of move away from the PhD. So in terms of the adaptation, which was the feedback mechanism, so for that I used fuzzy logic, which is a technique which is used for in intelligent controls. It's a technique that you can design that allows feedback. And like I said, control is all about feedback. What feedback allows, as a concept, what feedback allows is to adjust a certain level. So, for example, if I give you an example of, say, so you have like an open loop system. An open loop system, it says if you set up a level at a certain point, like say if you want the quality to be 3.5, which was what was acceptable at the time, then it continues to be 3.5. But if there is a disturbance that takes place, and that quality, and in this case the disturbance would be network, and that quality then drops below 3.5. If you don't have feedback, then you wouldn't know that the quality is actually dropped. And so what feedback allows is, once the quality drops below 3.5, the feedback then allows it to readjust and then takes it back to 3.5. So you have a split second, or there is that, whatever that time is, where your quality will drop, and then it will readjust, and then it will come back to that acceptable level that you have set up within your network. And this is quite a standard practice now for a lot of these streaming applications. What they do is they have these kind of forward error correction, as they call it. So basically you're watching a video, and because of network or some other reason, there is a disturbance which then causes the quality to drop. So for the user or for the consumer, you have a split second, something happens in a split second, and then that quality is then it comes back to an acceptable quality, perhaps not as good as if say you were at a level 4 or level 4.5. It may not be as good as that, but there is that compromise that what is acceptable, so it will go to an acceptable level. So for the adaptation scheme, so basically the control allows you to adapt. So for the adaptation scheme, I chose two inputs, congestion and degradation. And for congestion was calculated from the network, so the blocks lost over the blocks send, and the degradation was calculated from the mean opinion score. So basically, at a given point in time, you have a maximum mean opinion score, and the maximum value can only be 5. And you then subtract the mean opinion score that is at that point in time, and then you know what that difference is, because that's the degradation of your quality. And then with the two inputs in the fuzzy logic, you have one output, and the output is that I am just changing the center bit rate. But there are other things that, you know, in this whole area of forward error correction that you can also change, but you know, that's what I focused on. And then you have got your so this just shows you the triangular functions for the fuzzy logic and the different you know, how I define those triangular functions and the membership functions within that, and that's the output, which is dependent on these two inputs. And then again with the way the fuzzy logic works is you have your linguistic variables, so you have to define those linguistic variables, and these kind of variables stand for, I think, 0, small, medium, and large. That's the level of error. And then these stand for no change, very small change, big change, something like that. And so because fuzzy logic mimics human behavior, it gives you, it's a multi-level logic, and it's the best that comes to like that you can train the machine to have that human reasoning, because the machine or the way the computer works or worked, it was very much like binary, and binary is 1 or 0, so yes or no, and you had nothing in between yes and no. But the concept of fuzzy logic is it does mimic human behavior, so you do have in between logic, so it's basically multi-valued, and the way it works is you then define values between 0 and 1, like 0.2, 0.4, 0.6, or whatever, depends on how many levels you want to have. But then each level is an incremental increase or an incremental decrease, and that way you are making the machine to mimic in some way how a human would behave. And then based on that, you can then, so because like I say, my focus was very much on calculating or changing the sender bit rate. So you then calculate the new sender bit rate based on the old sender bit rate plus the change in the sender bit rate. And then what that did is that then allows you to keep the, introduced a feedback. So then it allows you to keep the video quality at that acceptable level. Okay. And then obviously to kind of validate my results, you sort of like run it with some of the video sequences. So Foreman was one of the video sequences which were like publicly available by researchers, and that's one of them that I used for my experiment. And this diagram here basically shows, how the MOS is basically adapted or with the Foreman. So there are 3 figures here, one where it's a red one and it's not adapted. So as you can see with time, when there is degradation, the quality just falls. And here it just shows you that the dotted blue line shows that there is a blip, and then after that it sort of picks up to an acceptable quality, and wherever there is a network blip, it will then pick up to that. So sorry, the dotted blue line, yeah, is with one of the algorithms, TFRC, which was again the standard algorithm at the time, and the black line is with my fuzzy logic, and so you can see the fuzzy logic performs better than the TFRC, which was the one that I compared it to, because that's another thing in especially when you're doing PhD at that level, is when you say that you've done something, this is my contribution to knowledge, and you know, this is my model or this is my feedback mechanism, then the obvious question is, why do you think it is better than the one that's already there? So you then try and show a comparison of whatever the state of art at the time was. So if TFRC is state of art at the time, that's what it was, but it must have been anyway, but it's a long time ago. Then you compare it to that. But if you are doing this research again today, then you would compare it to whatever the state of art today is, and then you would say, well, the reason I say my algorithm is better because, you know, it is outperforming such and such. Okay, and then this one shows you with the link bandwidth, I believe, and it shows the adaptation of SBR, the center bit rate, and the red line here is from the algorithm, and the other lines are at different center bit rates and how the bandwidth impacts on the mean opinion score. So it just shows that the adaptive video then, adapts the delivered video to the available network downlink bandwidth for that at different rates. Okay. So I think in a way that's all I wanted to say about my PhD. I hope that that's given you a little bit of background into where my research journey started from, and a bit of background on the types of things that I did during my PhD. So just to kind of give you a flavor, that I did publish around 17 papers, I think. There were about 7 or 8 journal papers. The rest were conference papers during my PhD, and a couple of my papers have got citations over 400, 500, because like I say, at the time, these were quite novel ideas, and so other researchers who have started, who started to work in this area, a lot of them, they sort of like refer back to what I'd done, especially bringing different layers of the OSI model in my own mean opinion score model, and it kind of lays the foundation to further develop work in this area. And it's sort of evolved. I mean, I don't think you kind of look strictly into this anymore, because obviously we've moved on from there. The network has improved significantly, but the issues still remain. You are still looking at quality of experience in different ways. You're looking at cloud computing. You're looking at how this very large or big data, as we call it, how we can sort of like, find ways to store it, but also find ways to, to maintain the quality. And that's where, in terms of networks, there are new and emerging networks within cloud computing that load, and also the point of failure, that if one cloud goes down, you don't want the whole network to sort of fall away. So what I want to do now is I want to just talk about the funded research projects that I have, or I'm working currently on in my current role. So there is so like I say, I started from video quality assessment, and from there, a lot of work that I'm doing now is on image recognition. So the EPSRC funded project is in partnership with Imperial College. We're just sort of like finishing that project now. So that was very much looking at, recognizing damage in the wind turbine blade for offshore renewable energy. So one of the things, especially here in the UK, is a commitment to net zero. I mean, as you know, electricity, you have you already live with those issues of having load shedding, and that is a big problem. The way we generate, or majority of the countries generate electricity, is we use non-renewable, oil and fuel and that sort of thing. So there's a huge reliance on those countries that produce that. Especially here in Europe, even before the war in Ukraine, there was a commitment to kind of move away from non-renewable resources and go into renewable sources and try and develop them more. But since the war started, a lot of European countries have recognized now that their dependence of oil and gas on countries that are very volatile is perhaps not a great idea. So it's all about forward thinking and planning. So there is a plan of what they call net zero by the year 2050. and they have put certain markers. Like I say, unless you make a plan and you put metrics in, you don't really achieve that. And we do that for EDI here, and it's now also being done for net zero. So by 2030, there is a roadmap. In that roadmap, by 2030, you have to achieve, certain cuts in emissions, and then by 2035, it increases by something more, and by 2040, etc., etc. So it's not like, by 2050 we will achieve it, and then you kind of forget about it, and then in 2050 you wake up and ask the question, what's happened? So one of the things in the UK that we have is it's a cold country. It's a cold country. There's a lot of wind. So the wind turbines have been set up in areas where you have hills, you have higher locations, and they have been there, and that's a technology which is old now. It's trial and tested, and it kind of works. Of course, you need to have wind. As long as there is wind, it works. But there has been like an environmental issue, because if you put them on mountains and hills, they're not pretty, so they do impact visually on your surroundings, because they're huge structures. So then there was a drive to put those wind turbines in the sea, because as you know, Britain is an ocean, is an island country. So we're surrounded by the ocean, the Atlantic Ocean, and there's coastline, and there are seas all around us. So the idea was, can we actually have these wind farms, but we can put them somewhere offshore, so they're not right on where people will go and enjoy the sea. They're further down, and so there have been the government has invested and given incentives to companies to put these wind farms in. So we have a wind farm in the south, so near Brighton, in Cornwall. There is a small wind farm in the Irish Sea in an area of Wales. There are these, and obviously Scotland. Scotland produces a lot of renewable energy from wind farms. But as you can imagine, they are located in very harsh environments. The sea is very harsh, especially at the North Sea, where we are. It is very harsh, because the weather can be quite extreme at times. So the maintenance of these structures can be quite a challenge, because the way they are done currently is, there is a boat or a ship that goes out to sea. The engineers wait for a good window of weather. So because if they go there and they realize, the weather is not very good, well, obviously they're not going to risk personnel, then the device has to be shut down, and then it's you have to put proper harnessing to climb up those structures. They're very tall structures. For the safety of the personnel, and then you go and you find out what the problem was, and then you go again to go and repair whatever that problem was. So it's not an easy task, and it's not a cheap task. It's the whole process is actually very expensive. So off late, there is momentum building up now to see how artificial intelligence can help. Can we do things autonomously? Can we have these structures repaired, or the maintenance of these structures? Can we do it in a way that we can reduce cost and reduce the risk to human life? And hence this project that I was involved in, and I'll share that a little bit later on, is all about. So that's a little background to that. These ones here are funded by the European Union. So there is obviously Britain is no longer in the European Union, but when it was in the European Union, we did get quite a lot of money from the European Union for research and innovation and development. So there are 3 projects that I am involved in. This is money. This is legacy projects now. So one of them, Marine Eye, which is this one here, will finish at the end of this year. And then the Celtic Sea Power, which is the Cornwall Flow Accelerator project, that will finish next year. And then there is so they are both very similar, where I'm looking at either the navigation and control or the, how we can use artificial intelligence, machine learning in intelligent ways to look at anything which is like underwater, because that's or within the renewable energy domain. And then we have this one here, which is the EPIC project. So that would finish in 23. I think that finishes in 23 as well, probably. And so it finishes probably in end of next year. And that's a very different project. So that's again funded by the European Union, but is funded. It's like it's all about health. So it's a very different application area. So I think it kind of gives you an idea of the breadth of application that I sort of work in, but also how powerful AI is, because if you are working within AI and machine learning, it sort of cuts across so many fields. So this is more about empowering people. I mean, Britain is an aging society. So what that means is we have more older people than the younger people, and people live a lot longer. So it is about improving the quality of life as people get elderly, and how you can empower them so they are living independently in their own homes, but obviously have access to healthcare very quickly. So it's like use of technology to improve well-being, and use of technology in a smart way that you can have. Say you can have intelligent sensors, IoT-based, Internet of Things-based sensors within the homes. You can put them in where they can detect fall, or they can detect how the elderly is, but it allows the elderly to kind of live independently and be, because obviously it's all about your pride and be able to feel that you are still productive member of the society. And that's very much using Internet of Things and sensors and sort of like analyzing sensor data. So that's the EPIC project. And then there is the project that also is coming to an end of this month. But I do have more funds to carry on a little further. So that's the Taxonomy Project, and that's funded by the British Council, and it's working with the university in Multan, Mohammed Nawaz Sharif University, and it was a fairly new area for me. It was in the agriculture sector, because like I say, I've never really worked in the agriculture sector before. So it sort of like opened my eyes to how, I feel so privileged to be involved in that project, and we're partnering with SAWI, who are based here in the UK, but they're working, that's knowledge transfer. That's a perfect example of how industry and academia can work in partnership to transfer that knowledge on the field and make a difference where it is really needed. So you've got the impact of climate change. I mean, Pakistan, 70% is agriculture. That's how the GDP survives. And you have water shortage. There is a big issue of pesticide use. There's lots of issues within farming. Of course, some are man-made, and some are man-made in a sense that they are man-made, but they are climate change. And if it's not raining, or the whole impact of climate change has got a devastating effect. But then some are also the behaviors of farmers, not because they're doing it on purpose, but because it's a lack of education. It's not understanding how to best use resources. And I think that's where smart farming, or bringing AI into farming, can make such a big difference. And again, I'm working on machine vision and how we can identify diseases in crops. I mean, one of the other works I also did, which I will share in a little bit, is applying computer vision. But I worked with the university in China, where we analyzed lung X-rays of COVID patients, and we saw how can we actually segment those lesions of disease and make it easier for the healthcare providers to make those diagnoses. So you can see AI has got so much application, and it goes across the areas of where you want to apply, and it's it keeps it interesting for me, and I sort of keep dipping my toes, as I say, in different areas. I wanted to share this slide because this is the United Nations Sustainable Development Goals. I think we were making good progress until COVID happened. So there are 17 goals, and these are goals about, empowering developing countries so they can actually have access to good health, quality education, gender equality is in there, clean water, sanitization. I mean, these are the basics and the fundamentals. That is what is a human right. So it's not a privilege. This is not a privilege. I mean, for me, this is a basic human right. But obviously, COVID happened, and a lot of the progress that was made was reversed. And then, sadly, as we were recovering from COVID, there is a war in Europe, and a war in Europe because Europe is the developed part of the world, but it has consequences on the developing part of the world, and everybody is feeling the shockwaves of that wave, whether it's in terms of inflation, whether in terms of cost of living, whether it's in terms of food shortages. It's just absolutely crazy. But it is useful to know this because, especially us as researchers, if we are looking to go into a new project, it would be useful and helpful to know how it links with the UN SDGs, and then it makes it more kind of empowering for the researcher, and obviously in terms of impact on the people that you are trying to make. So I do have a question. So if I go and if I stop sharing this and share my Mentimeter, so it's similar to what we did yesterday, and I will just share my screen there as well. So my question really to all of you is that, are you aware of the Sustainable Development Goals? And for those of you who have just joined today, if you go on the website www.menti.com, and we'll ask you for a code. The code number is this, 83139744. I can put that number in the chat as well, so if that helps, 83139744. And then the question should magically appear on your screen. And it's just for me just to try and get a feel of all of you, whether you are aware of these Sustainable Development Goals. So cool, that is good. So I could just wait for a minute or so. See if anyone else wants to come in. Okay, well, it's there. The Menti keeps running in the background, but it's good to see there is awareness of that. So like I say, I want to kind of focus on the recent research that I'm doing, and that is very much, I've sort of focused on where I am using computer vision. So I started, and these references here are published papers that we have published, where, in this sort of field. So we have got some sort of track record in this area. So when I started my lectureship here at the university in 2015, I teach mechanical engineering students. I am an electrical and electronic engineer, and I teach them control systems, which is a subject or a module that kind of overlaps between mechanical engineering and electrical and electronic engineering. Research-wise, video quality, prediction, perception, that kind of research very much kind of overlapped between electronic engineering and computer science. So you can see the kind of the dilemma that I was in, because obviously I was sitting in with mechanical engineering with the research, which was kind of like in computer science. So what I did is I had to rethink and refocus and think how I can, repurpose my research in my current role. With mechanical engineering, the one thing that the trial started in America with Google Car and Tesla of autonomous cars, and obviously there are autonomous cars, Google Car, which is like being driven in America, and I don't know how many miles it's done now, but that so the car drives itself, but there is a driver that sits in just in case something happens. But they have had accidents, and obviously I think from what I've heard, the driver had fallen asleep or something or other. Basically, the driver didn't take control, and that's why the accident happened. But having said that, the whole point of an autonomous car is that it should recognize if there was an object that came right in front of the car. So you can see computer vision plays a massive role in autonomy, because the whole point of autonomy is you're making decisions. A computer, the machine is making decisions. If the machine can see, if the machine can hear, if the machine can sense. Now, how does a machine do that? The machine doesn't have eyes and ears and nose and that kind of thing. So you give it sensors, and camera is one of the sensors that you give the machine. So one of the things we did is the UK also started the trial, and that is in a place called Milton Keynes, which is near London, and there is an autonomous car there that sort of like is driving and collecting data. Because the idea is that the more you drive, the more you collect data, and then it helps the machine to learn from it, big data, and then the algorithm improves. So what we did is we took a mobility scooter. A mobility scooter is people who cannot walk properly. The government gives them like a mobility scooter that you can then sit on. The maximum it goes is 5 miles per hour, and then you can kind of gives you that independence that you can go to the shop, so you can go out and so it's like very, very low speed. And you can do a few things with it. So we acquired one of those and we stripped it, and then we converted that into an autonomous buggy. We have put ultrasonic sensors on it, we put Lidar on it, and then we kind of like simulated some experiments with students being the pedestrians, or cardboard boxes, and so we, in very controlled laboratory conditions, we did that, and that vehicle is there. Which we can use as a test case for many things now. So we published a couple of papers on that. So I'm going to talk a little bit, and I'll show you what the vehicle looks like. Like I said, the Lidar data visualization, that is also on the vehicles. That was the test bed, and that enabled us to look at that Lidar. And why that was important and relevant is because I'm sort of more going into the offshore renewable energy research, and there also the Lidars are used with drones. So any knowledge that we gained from using Lidar on a land vehicle can easily be transferred into, say, using a Lidar within an aerial vehicle. Of course, your navigation and control is very different to an aerial vehicle compared to a land vehicle. And then the detection of damage on blades and wind turbines. So that's what I kind of touched earlier, and I will go a little bit further. Segmenting small infection regions within an X-ray of COVID-19 patients in China. So that was quite an interesting bit of work as well. And all of that is using computer vision. And then finally, the detection of disease in cotton leaf, which is the British Council funded Taxonomy Project in partnership with Mansour and Sawi. So that's that just shows you kind of the range of application of computer vision. And obviously this is not exhaustive. This is just what I've been involved in. I'm sure there are many, many, many more applications, and it depends on interest and opportunity. How where perhaps researchers are involved in more of this. So let me just go back to the Mentimeter, and I do have a couple more questions for you. So if we go there and go to the next one. So this is a question for, I mean, I'm very aware that very few people are getting involved in this, so perhaps I may not get a representative answer there, but I just wanted to ask if your research or teaching does involve AI or machine learning, because if it does, then the relevance of what I'm saying perhaps becomes a little bit more important. Otherwise, I would say it's perhaps more transferable and something that you may want to get involved in after you graduate. Okay, so that's interesting. So that's one said yes, one said no. So, but at least someone is involved in AI. Perhaps at undergraduate level, maybe not, but maybe if this kind of tickles your mind and if you get excited and you are thinking of post-graduation, then with the sound physics and chemistry degrees, it's something that you can very easily transfer into. Okay, so got a bit more, so that's nice to see, 50-50. Okay, and one more here, which is, does your research or teaching involve computer vision? Now, AI, as I say, is very broad, and it involves deep learning, machine learning, unsupervised machine learning, lots of different things. Computer vision is very specific because you're very specifically looking at cameras and images, and what comes out of those images and how you can then make some sense of that, or how you can recognize it. So again, it's a binary yes, no, one if it does. Oh, cool. So at least one person does. That's great. Okay. So cool. And again, with the background, with the what you're studying, if you are at undergraduate level, if you go into post-graduation, very easily you can go into computer vision. I mean, I would say go broadly into AI and then focus on computer vision rather than just go into computer vision, because computer vision is just a part of AI. And the references that I had put with the papers that I talked about, you can see, I've just listed them here, so they're all here now. Okay, so autonomous systems, just a couple more slides, and I think we could take a short comfort break then, maybe 10 minutes and then come back. So a definition of an autonomous system, it can perform desired tasks in unstructured environments without human guidance. So that's what an ideal autonomous system is. Obviously, we're not quite there. We're probably there in some very well-defined applications, which are like robotic arms, or in Industry 4.0, the whole kind of like use of robots within an industry setting, where a robot is told to do one task and it does that repetitively, and that works in that environment. But when the environment becomes, but that's a structured environment. But when that environment becomes unstructured, like say an autonomous car, where it has to navigate to left and right turns and, understand people from animals, from poles, from traffic lights, from pavement, that becomes more complicated for a machine to carry out. And without human guidance, I mean, it's not something that we have fully achieved yet. I know in the marine sector, because 70% of the trade is done over the sea. So that's, again, one of the projects with the ERDF funded projects that I'm involved in. So 70% is over the sea. So within the area of the sea, you have very structured lanes. So what happens on the road is very chaotic, and there's a lot of noise, because you have buses and you have taxis and you have cycles and you have cars and you have motorbikes, and humans make mistakes and errors, and obviously that brings its own challenges. Whereas what happens in a what happens in a on the sea is you have very well-defined lanes, and with very well-defined lanes, what is useful and helpful is it is easier to apply autonomy there. And so within the marine sector, there is a huge push and there is a huge sort of like research going on currently is, can we make those, especially the goods, the ships that brings goods, can we make them autonomous? Because what happens is you would reduce the number of personnel, or I mean, you would probably still have a level of personnel there, but you really significantly reduce that. And, you know, the way the ships are operate, because they operate in very kind of laned way, it is easier to implement the sort of like machine learning on it. So just to give you an idea of the classes of autonomous systems, you have the basic, which is a human operated system. So human tells the system exactly what to do, to the top, which is a fully autonomous system where, you know, it just does everything itself. And in the middle, you have a system which is human assisted, or human delegated, or human supervised, or you have something which is like a mixed initiative system. So it just gives you an idea that we have different levels or different classes of autonomy, and we are not really at this final stage yet. It will take a leap of faith in humans to fully trust the machine, but it will also mean that the infrastructure has to be updated to a point that you can trust the machine to carry on the tasks that humans do effectively. So for example, even in medicine, you have levels of autonomy, which is used. Robots are used in surgery, they're used in many things, but they are more like human assisted systems, or they are sometimes human delegated systems, but you have an involvement of humans there. Okay, and just to kind of show you within autonomous systems, it's from the Royal Academy of Engineering. I think they produced this diagram. I quite really like it because what it shows the four corners here, the four corners of intelligence. You need control, because control brings feedback. Because if you can't control something and continue to control it, you've kind of lost it. And then you have cognition at the bottom here. So cognition is it's how you make decisions, your thinking process. So what it's saying is you have an insight about something, and then you make your decisions here. So that's management and orchestration. Decision leads to an action, and then you have some results. And the results, the control comes because of sensing, or I suppose the feedback comes because of sensing. The sensors tell you, oh, something's going wrong. I need to readjust. So you sense and measure, which gives you the things, process, and context. And then you kind of feed into the data, which could be structured or unstructured, and then the loop carries on. So there is analytics there is learning and optimization, and there is automation. And this is an interesting one here, policies and rules, so ethics. It's initially when we talked about, going back a few years, when we talked about machine learning, when we talked about artificial intelligence, ethics was never considered. But what's now happened is, or what's now happening is, a lot of these algorithms are developed by a certain race, are developed by men. So biases have been, inadvertently, perhaps not consciously, but unconsciously have been put in. And an example of that bias was in Uber. Uber is like a taxi types organization, which allows people to kind of register, and then you can run your taxis. And what happened here in the United Kingdom and in America is the facial recognition algorithm that Uber was using, they had problems because they were recognizing certain colored faces, and they were saying, oh, you have a record, because they were matching it with their database incorrectly, and the database was matching the saying these two are the same. And so they were like, obviously denied their license. But that highlighted a whole issue of ethics, and where you are now looking at automation, where you're looking at autonomy in general, it is very important to think of ethics and think of how you build in against the unconscious, or in some cases maybe conscious, bias that may be put in by the operator. Because remember, the machine is only as good as a person designing the machine. And then as the machine is learning from the data, the machine is getting better and better, or the algorithm is getting better and better. So I think that was an interesting example of, you know, the kind of lack of ethics within that. Okay, so I think, let me just stop sharing it at this point. I think it's about 10:40. Perhaps everybody may be feeling a bit tired. Can we just have like a 10-minute break and then start again at 10:50? Would that be all right, Dr. Aksa? Yes, can anyone let me know that it's all right to have a 10-minute break? Or can anyone just write in the chat? Just confirm. Yes, okay, thank you. Thank you, Dr. Farah. All right, so I am just going to stop my video and unmute, and I'll come back in 10 minutes. So here it's 10:50. So over there it's probably what, 2:50 or something like that. But anyway, I'll see you guys in 10 minutes.
Recording stopped. Recording in progress.
Okay, are we ready to start? Can anyone put it in the chat or just give me a thumbs up that you're back from the break and we can start again? Okay, no, thank you. Thanks, Dr. Parab. Okay, so let me just share my presentation again. And where were we? We were here. And let's just put it into mode. So, yeah. So going on to artificial intelligence. Oh, thank you. So what is artificial intelligence? I mean, it is such a broad word which is used. Obviously, it sits within the field of computer science. And artificial intelligence means that humans have intelligence, they have cognition. But what you're doing is you are enabling the machine to think and learn like humans. So you're giving them that artificial intelligence and cognition. So that's why artificial intelligence is very broad and it's very big, and lots of things kind of fall within its remit. So things like supervised or unsupervised machine learning, things like reinforcement learning, all of that is within artificial intelligence. Machine learning is a bit more specific because you are now kind of getting into the nitty-gritty, and you're saying you want the machine to learn in a specific way. So you can ask the machine to learn in what is called an unsupervised learning. So an unsupervised learning is the data that you're giving to the machine is not trained in a way that it's like, it needs that structure, and hence it becomes unsupervised learning. Things like classification, clustering, they are unsupervised machine learning. Then you have your supervised machine learning, where you are giving a structure to the data, you're defining categories, you're saying, well, that is within this category, learn from this category. This data is movement data, this data is, sensing data, this data is images, learn from those, and that becomes a very kind of supervised way. And within a Venn diagram, what you have here is semi-supervised. So semi-supervised is there's a bit of supervision, but not full supervision, and that's what that would imply. And then you can also have self-supervised learning within that. And then what we call reinforcement learning. And reinforcement learning, you can see, is a circle within itself. And reinforcement learning started as the data started to increase. So what you're saying is you're telling a machine to learn in a particular way, but then you give it more data, and that data reinforces a certain learning behavior because you want the machine to or adapts or adopts a new behavior. And that's what the name kind of suggests, that you're reinforcing certain ways of learning. And deep learning actually kind of like overlaps all of those. I mean, some people would say that deep learning is very much between supervised learning and reinforcement learning. But things like self-supervised learning or semi-supervised learning, they would also sort of, fit within the deep learning. So computer vision, where does that fit in? So within artificial intelligence, you can see you have machine learning from the previous slide, and the machine learning then kind of goes into, the computer vision is a type of machine learning, but you are learning in a very specific way. You've got images, and from those images, you are telling the machine to learn something about that image. So broadly, it is within artificial intelligence, and it then becomes a type of machine learning. This slide here gives you a bit of the history of where it started from. So if you think about artificial intelligence, early artificial intelligence, it started from 1950s. So, even though in between 50s and 60s, you wouldn't have heard it that widely, because computers were very clunky devices in those days. And they used, they were very clunky, their processing powers were not that great. So while you had the concept of artificial intelligence, the implementation kind of started from the 80s, when you transferred that level of artificial intelligence and you found a way for the machine to start learning, with the what we call a desktop computer, as they started to come. So 80s and then 90s, 2000s, 2010, and in 2010 is where the deep learning came into play. So that's, and you can see the difference here. That's very much about like cognition. So you are trying to mimic human behavior in many different ways. And the way the deep learning is you've got like certain structures of neural networks, and you keep adding layers in certain ways, so you can then have you can learn more. And reinforcement learning is very much like this concept that comes from your deep learning. And what it says here is that has caused larger disruptions, and you can see why, because things like autonomous driving, they wouldn't even have been possible if it wasn't for deep learning. So some of the major milestones within computer vision is, again, like it says in the previous slides, 1950. So the term artificial intelligence was first used in 1956. And some of the people, the pioneers, Hubel and Weiser, they discovered vision is hierarchical. So that was an important concept. And then you have got the first computer vision project started in 1960s, the MIT Summer Project. And I think when we look at these kind of timelines, what I find, for me anyway, what I find really fascinating is something that I think probably only came about 10 or 15 or 20 years ago. Actually, it's got history which is sometimes more than 100 years ago. And then it shows you how the evolution in science has happened in the West. Why? Because the infrastructures were there. Because what you need for research, you need an infrastructure. And within those infrastructures, once you set up those infrastructures, the research thrives in it, because you're enabling people to think for themselves. And then, you know, the laboratories and the experimentation and the data collection, the discussion between scholars, it enables, you know, certain discoveries. And as those discoveries are made public, it's like, you know, you stand on other people's shoulders. Someone else comes in, looks at that discovery and sees something completely new in that. And so you sort of like, you know, you go the next level up. And then in 1970s is when you have the AI winter, you know, that was the terminology that was sort of used. Viola and Jones, I mean, in computer vision, if you like, that's the kind of like, you know, pioneering of face detection. That is very, very widely used, and that started in 2001. So you had rudimentary neural networks started in 1990s, but it wasn't until sort of 2001 and then beyond that this kind of concept of deep learning started. And obviously deep learning 2012, that's the AlexNet structure. That was, you know, their paper, and they started this whole concept. And a lot of it now is publicly available. So if you go on things like Google Colab or on things like TensorFlow, you find a lot of fast CNN algorithms that are there, and you can then, you know, start to work with them. You can start to repurpose them for your application. So to give you so that's like the what we did with the COVID lung lesions is we used deep learning for image recognition. We used something which is called UNet. So before I go into the UNet, it just give you an idea of the visualization of DenseNet, which is a deep learning algorithm for image recognition. And you can see the way, so this going back here, so, you know, this is like AlexNet, and from AlexNet, we have lots of like nets that, you know, came after that. So what you have got, or what you are introducing here, is you're introducing this pooling and convolution, and you can keep inserting them. So you start from an input, which is an image of a horse. You want to predict that it's a horse. That's the idea of image recognition, is you give it lots of different horses, a new horse comes along, and it should be able to say, oh, that's a horse. So that's just very simple object recognition. Classification would be that you have a brown horse, you have a black horse, you have a, you know, a spotty horse or a stripy horse, or whatever different categories, and you should be able to categorize those. So you have a number of dense blocks. Each of these blocks, as you can see from the images, has got like layers of neural network. And then you insert convolution, you insert pooling. It's all mathematical, you know, there's a lot of mathematics involved in it. And you keep doing that until you can kind of fine tune your final prediction, and you're happy with that. So that's how in sort of block layers, very simply, to simplify a structure of DenseNet works. I wanted to just give you some definitions. Something that you hear quite a lot in computer vision is one of these things called image augmentation. So what is image augmentation is I have got a very small database of images. Let us say I only have, you know, 20 images, but I want to like train my neural network to identify those images from the 20 images. Now 20 is a very small number to train your neural network. So what I can do is I can augment that image. So from that one image, you can see I've created 6 new images. So it is just augmenting it in, you know, sort of like different angles and showing the same, you know, face in different ways. So you can see that from the 20, I can produce 100, 150 images, and that gives me a good number to train my neural network. And so this is one method that researchers use to increase the size of their data. Another one is called image segmentation. The idea of image segmentation is you partition an image. So if you look at this image here, you've got a tiger, you've got a background sea there, you've got grass here, and you've got a bit of like, you know, grass disappearing, so there's a bit of sand. So what you do is you identify regions within that image, and with those regions, you can see that the green is the grass, that's the shape of the object there, and that bit there is this things here. So what you're doing is you are partitioning the digital image into multiple image segments, or they're also known as image regions or image objects. And then you can then get your machine to learn each one of this segment separately. The other way that we also do is we can use, so that's not image segmentation, but what we do is when you have a busy image, say something like that, and you want to identify an object, whether that object is a tiger or whether that object is a green grass or blue there or that bit there, you can have what we call anchor boxes. And so what you do is in your training, you label the image and you create these anchor boxes. And so what you're then telling the machine is, hey, look, there are these anchor boxes and I'm only interested in the box. I'm not interested in anything which is outside the box. So those were some sort of conceptual things. This is what there's a few papers that we have published, which is using image recognition, and we can kind of go over some of these. So this is the one that I talked about, the pedestrian recognition in autonomous vehicles. So what we did is we, once we repurposed the mobility scooter, we then used both machine learning and deep learning. So we used methods like HAR classifier and HOG descriptor, and they are methods which are already tried and tested within research, basically, and in literature you can find them. And we used the image recognition. We used database which is already there to train the algorithms. And then what we did is we used deep learning. So for deep learning, we used the single shot detection method. And the sort of flowchart here shows you what we were doing. So you've got, you import your packages, you declare your HOG and HAR tool, and then there's a bit of a loop. If the pedestrian is present and if it's true, you then draw rectangular boxes around the region of where the pedestrian is. You go back and you carry on, and if it's false, you again go back and you carry on in a sort of like in a certain way, display your final image, and that basically ends your program. And what we found for this particular one is that deep learning gave us the best results. So here, going into all of those, rather than doing all of those in detail, these are the results of the HAR classifier, the HOG classifier, and the deep learning. And you can see that the deep learning outperformed the two machine learning algorithms. So what you can get is you can get a false positive, you can get a false negative. So a false positive is when it's not a pedestrian, but it's telling you that it's a pedestrian. A false negative is that there is a pedestrian, but it's telling you that there is no pedestrian. And so those are the kind of important things that you need to consider whenever you're doing image recognition, and obviously then there is a success rate and that you measure it by. But like I say, there is always a caveat with these machine learning, is they can only perform as good as the data as you supply it to. And if there is new data, if the environment of that data changes, then your algorithm also changes. So this is the vehicle that I was talking about. I'll just play a short video here. So I just play that. Playing. Not sure why it's not playing. Just move that forward. Let's start again. Try it one more time. If it doesn't play, I'll just move on. Okay, so I'm not really sure why the video is not playing. I just wanted to kind of show you, this is the mobility scooter that we repurposed. And what you see here is a Raspberry Pi. We use a Raspberry Pi as a controller, connected it to the mobility scooter. And obviously these are some ultrasonic sensors. And then there's a Lidar there that we also connected to it. very strange. Oh, okay. And the LiDAR that we used was a Hokeo LiDAR, and it was a 240 degrees field of view, so it was a 2D LiDAR rather than a 3D LiDAR. And the LiDAR was also connected to the Raspberry Pi 3. So we used Python to write the code for this particular application, and for the LiDAR specifically, we used a robot operating system, which is also called ROS, and that system is within the Linux environment, and for that we use the light Ubuntu, and what that does, it is like a standard operating system that is very much used for, well, it is used for a robot application, but also Raspberry Pi is also a Ubuntu type Linux operating system that you can then use. Okay. And this here just shows you some of the images that we took from the LiDAR. And again, there is a publication with that. Okay. Sorry, I just went into the chat. I thought there was something there. But thank you for the feedback. I think it's very helpful for me to get that feedback from you guys, because I hope that it will inspire and benefit you guys, and you've learned something new from what I'm trying to present. Relate it to myself rather than present something which other people have worked on. So that's really why I sort of like did my presentation in a way that it was my own work, or I say my own work, but work in which I'm involved in, because you never work alone in academia. You work with teams of people, so they work with you or you work with them, and that's really how you get good research, but where I'm involved more actively. So what this shows is the LiDAR images. So that's the buggy, and that's the pedestrian. And what we did is we created different scenarios, because if you think of a LiDAR, it's a light imaging device. And one of the problems with a light imaging device is if you have reflection. So imagine if a LiDAR is connected to an autonomous car. The autonomous car is driving on the road and there's a lot of rain. Ooh, how would the LiDAR perform? Because that can cause problems, because there is reflection, there is, the line of sight is blurred. And so what we did is we created some scenarios where we added reflective tests, where we put like a tin foil to create a reflective test. Then we made an angle to the reflective test, and then we did a stationary test, and then we lowered the light, and we saw what that is doing. And you can see that bit is fine, but the dots that you see is that the LiDAR is picking up images, or it's picking up something which doesn't exist. So there was nothing where the two dots are. So that's kind of false positive. Similarly here, the LiDAR picks up two dots, and that's again another false positive. And here, the LiDAR is picking quite a lot, so that's a low light test. So in the low light, the LiDAR is seeing lots of different images here where the dots are, because it makes a point cloud of the image that it's sort of detecting. And again, here you have a point here that shouldn't be there. I mean, this is the vehicle, so you would expect the U or the rectangle, the half a rectangle, to be there. So that's perfectly fine. But these dots that you see additional are all false positives. And that was interesting because, I mean, this is done in controlled environment, and I suppose in a controlled environment, it is how we were emulating certain scenarios, and that obviously, the LiDAR is a 2D LiDAR. You can have 3D LiDARs, which are a lot better. So there is obviously there are some limitations of the way the experiment was conducted, and it was interesting that some of these results weren't as we would have expected them to be. And this is the one that I wanted to share, which is the detection of damage on blades in wind turbines that I was talking about. that this is my more recent research, and what we've done here is I've sort of, within the offshore renewable energy field, when you have these wind turbines, if there is a damage on the blades, we want there is a industry drive to actually try and automate some level of maintenance. And so a repair is obviously, we're not there, repair is miles away yet, but can we actually identify the faults autonomously? So if we know that there is a damage and that can be done autonomously, then we can send an engineer to just go and repair the damage. So you actually save one trip, which is the observation trip, to understand what the problem is. So the way the concept is you have drones, and you fly the drones around where the wind farm is, and the drones fly close to your turbine. Obviously, you switch the turbine off. You fly the drone very close to the turbine, and the drone has got cameras, and those cameras will take images of the blade, and you can have either within the cloud or on the actual drone, you can have your algorithm that recognizes the damage, and as it's sort of hovering around, either it does it in real time, or it does it offline, as if you take the drone back. It just takes lots of different images. You bring the drone back to a surface vehicle, which is obviously on the sea somewhere, and then you put the drone images in your computer. You analyze those images, and your algorithm tells you, hey, turbine number 2, because you need to, from the images, you need to be able to identify which turbine, because otherwise it's pointless. So turbine number 2 blade has got a damage, and then you can first identify the damage, and then you can classify what that damage is. Erosion is one of the more common ones that you get on those wind turbine blade. So what we have got at the University of Plymouth is we have got a massive coastal laboratory, and that laboratory has got like an ocean basin and a coastal basin. So what I mean by that is we've got like a 35 meters by I can't remember so 35 is the length, and I think it might be 12 or something like that meters. I can't remember the width exactly. And we can then emulate ocean currents. We have got 12 individual pedals, and that emulates the ocean currents. And that's a picture that you see there. On the ocean basin, what we did is we put a floating wind turbine structure, and that is the blade of the wind turbine. And we simulated some of these faults ourselves, and then we developed an algorithm which was based on fast RCNN. It was a MOBNet model, which is already there in PyTorch, and we used TensorFlow to run those images. And what you see here is the label of the images here, and then basically what you see is the algorithm then is running and is evaluating. And you can see here it is worked well because it has identified all 4 of those, but here it hasn't really identified this, but it is identifying that as a blade image, but it's not. I mean, it's as you can see, the problem with this is there's a lot of like background. It's a busy background because that's the gantry behind the lab, and you see a lot of like reflection as well. So all of that has an impact on your computer vision algorithm. And this was the first cut that we did, and it was a very interesting project, and obviously it was a lot of fun as well because you're playing with the real stuff rather than still in a controlled environment, not off on the sea or anything like that. But I think when you have got hardware rather than software, you can visualize things, and that is pretty good. So this is, I hope it plays. Okay, so that is not playing. I really don't know why. Let me just stop sharing and find a file that I can get that video, because it's a good one to just watch. The drone flying. Let me just see if I can find. Oh, it says it cannot play media. Just give me 2 more minutes, see if I can play from my OneDrive. Otherwise, we just have to. I do apologize for that. I had checked it and it seemed perfectly fine. So I don't really know why it's kind of playing up. Okay, so it's playing there. Let me just go back and let me just share my OneDrive. Okay, so let's just play this. So there is a noise. Ignore the noise. So that's the drone. And you can see the whole structure of the lab. So that's the mute that. Yeah, I've managed to mute that. So the noise is gone now. So what you can see is that was the landing pad for the drone. That's the drone there. That's the lab that you can see the water there. And that was the wind turbine structure that we put on the lab. And you can see with this blade here, we have put 3 blades for this one here. We emulated some of the falls. The drone sort of like flies there. And so that's the kind of like scenario that we wanted to show and demonstrate at a conference. We did that. This again got a Best Paper Award at the Control 2022 conference that we presented. And it's one of the principles that we want to take this project forward is to show repair. So on the drone, you can have like a nozzle fitted. And so again, if the algorithm is working in real time, then what you can do is you can you see how the drone gets close to the image there, the blade there, looks at the image, and then it says, there is a damage there. And sometimes the damage is just a bit of dirt. So if it can then spray something, which then cleans the blade, at least that would then save one of the trips for the engineer to actually go and repair that particular wind turbine. And you can imagine that this is happening at sea, and sea is a very harsh environment. So what you see here as a landing pad would be like a surface vessel, which is just kind of anchored very close to where the wind turbine farm is. And then they would just be sitting there. And if the weather becomes hard, they kind of go back to safety and then they come back. So they could be at sea for like 3 months. So clearly there is a risk to personnel, but there is also a huge amount of cost involved in the whole kind of maintenance process. So once a drone has done that, the drone kind of flies away from the wind turbine, and then it will come back and it will safely land to back to its sort of like landing place, which is what it is doing now. Okay, so if I can speed that up, so you can see the drone is there, and then it kind of comes back, and then I can go back to my presentation. It's still hovering around, looking for more, and obviously if you have turbines, you would want the drone to go, because in a farm you will have lots of wind turbines, so the drone will carry on and it will then go and it will do that. So that is a lab that we have within the University of Plymouth, which is an excellent asset. It took £19 million to build this facility. So you can now see the drone sort of coming back, and the drone will then land there. So it's a bespoke drone that is sort of made very specifically for this particular application. So I just thought it was worth having just to kind of see if I can find the video. I still don't fully understand why it doesn't work it didn't work for my, so yeah, let me just go back to my presentation there. It's this one there, so that didn't work. Okay, so that was that project, and then, oh, yeah. Just showing you a bit of the COVID images that I talked about. So here we used UNet. So again, the concept was added UNet. The concept here was you have input images, so they were the images of the lungs with diseased lungs. You have a convolution pool, so going back to the dense net structure that I showed you earlier, and then you have your bit here, which is about what these are looking to. So this is like the convolution and function there. So convolution and pooling that is happening there. You have a bit of a transition there. So again, convolution pooling. You have your neural network there. And then you know there is a process that happens within the UNet, because its UNet is very specific and it's used more in the health area. You have this very layered structure, and then out comes the output images, which then shows you where the lesions are. So what we did there is it was segmentation basically of the diseased lungs. And the dense network is convolution and maximum function to enhance facial propagation, and it then solved that gradient disappearance problem. So that's, overall the integration of attention gates, where there was novelty here. I mean, there was novelty here anyway within the UNet, but there was additional novelty here that the attention gate dense network was then basically combined with the UNet, and that then improved the prediction accuracy of the infection segmentation. So again, these are tools that can be used by healthcare professionals to, COVID is one example. Obviously, it was at the time. It still hasn't gone away. It's not going to go away. But obviously, at the time when we were doing it, it was very kind of prominent, and so it just made sense that let's just have a go at it and see what happens. Performance accuracy in terms of accuracy and precision was very good. We got accuracy of 97%, but precision and F1 score were about 84, 85%, 82%. So the idea here was to show that it can aid clinicians in faster screening and quantification of the lesion areas, and so it provides an overall improvement in the diagnosis of COVID-19 lung infection. And this is the current one that we are working on currently. So we're still looking to develop computer vision algorithms on that, so we can identify cotton leaf curl disease in the cotton plant. So the idea here is we have collected images of healthy cotton leaves and images of diseased cotton leaves. So that's the leaf curl disease, and you can see the challenge here is when you have got like diseases like rust or any other disease within the leaf, where the color of the leaf discolorizes. So basically the green of the leaf becomes yellow or pigmented or red or whatever. It is very easy for the machine to pick up. Why? Because there is a difference in color, and you just focus on the color there. But with the leaf curl disease, as we are finding, as we are developing the algorithm, it is quite challenging, because what's happening is the leaf color hasn't changed, but the leaf curls. In some areas you can see that the vein of the leaf, there are bits that you can pick out, but the curling is something which is not that easy for the machine to actually work with, but is something that we are currently working on, and hoping that we can get some level of decent accuracy in the predictions with that. I believe that we have got Industry 4.0. We've all heard about that, the bringing of Internet of Things and cyber physical systems, and that is coming. But that's already there now. But I do believe that the next disruptive technology is Agriculture 4.0, because in the field of agriculture, cotton is one area, but there is wheat and there is food production. Basically, it ties in so well with the United Nations SDGs, and in the whole area of agriculture, smart agriculture, there is a competitive advantage. There is the utilization of resources that, you know, they are so scarce now that if we can bring technology to help and improve that, then that is you know, that has to be a good thing. I mean, what I heard very recently is the UAE has invested or is investing $2 billion in India, in the farming industry in India, where they are working with companies from America and Israel. And basically, the UAE is just providing the money, and you can see it's a big amount of money in the region of $2 billion. But the expertise is coming from companies in America and Israel, and they are going to work with the farmers in India so they can transform the farming, because obviously India also produces cotton, India also produces wheat, India is also an agriculture country there. So it is something that we in Pakistan should really be watching out for, because we do need big investors in farming. We do need people to come and invest so we can keep up with the competition. Otherwise, I mean, countries like Brazil are already ahead of countries like Pakistan. But, you know, if our regional countries, our regional neighbors, if they start to outperform us massively, then you can see we will really be left behind in agriculture, and that would be a real shame. So it's first of all understanding, and then, you know, getting policies and trying to get the right people talking in the right way, sort of thing, and hopefully change will happen and it will bring. I mean, that sort of concludes my talk. So I do thank you all for listening, and, you know, obviously for having this opportunity to just share my own research experiences and, you know, what we have done to date. I mean, obviously this is just a start. I think computer vision, image recognition is massive. I'm, you know, very excited that I'm continuing to work with Mansoor, and we are developing this algorithm now that, you know, perhaps in some way, shape or form, you know, and if then with knowledge transfer in Savi, if that makes a difference, and other people, if the other players, they start coming, so that would be quite exciting. I think impact-wise, that would be very exciting. But I think hopefully it has given you a flavor of how artificial intelligence, broadly speaking, has an impact on so many different fields. And what we need to, we as researchers need to get into is, we need to get into different areas of artificial intelligence, understand what it is, and then apply that in our own context and in our own fields, and see how it can improve. So think of technology as a tool that improves the quality of life. And I think if you look at it like that, then everything that we do will come from a point of, we are looking to improve things for us and for people around us, for our communities. And from there, you know, at least there is a bottom-up approach. Research, you know, there is an environment of research that starts, it helps the people around us, and hopefully then we will get the attention of the people at the top. And so policies will happen that will then, you know, provide a conducive environment. I mean, here in the West, we're very lucky because we do get the right policies. I mean, not always, but if we don't get it, because there's democracies, people can stand and shout and try to be heard. But, you know, like the net zero, the whole net zero is policy driven. So that is driven top down. It's coming from the government. They have set an agenda. And then obviously organizations like us, we do research, but industry is the one that converts that research into real business and real money, and obviously creating that for the country, but also employment for the people. They are then seriously looking into or becoming serious players in that journey to net zero. So are there any questions or any comments or thoughts or anything like that? Dr. Aksa, I don't know if you are there, just trying to see through the list of names I've got on my screen.
Hello, I'm Professor Dr. Zora Kiani, Chairperson Physics. And I want to thank you for your very informative talk. And I hope all the students and faculty must have learned from your talk. Thank you very much for joining us, and looking forward to see you at some other occasion as well.
Thank you. Thank you for your kind comments.
Okay, thank you. Take care.
Okay, thanks then. Okay, bye. Allah Hafiz.